Hey y'all, it's Catch here. In this TidyTuesday video, we're going to continue our project from scratch, creating a UFC sports betting model. And my previous video, we did the data scraping and data cleaning part, and now we're going to focus on the feature engineering and modeling. But before I start this video, I want to go over a few things. One, I have a Q&A video coming up probably in about 2 weeks. So if you want to ask me any questions for that Q&A video, please click on the Google Drive link and submit a question. Also, so I usually record these videos in advance, and when I was doing the actual modeling part, I completed it on Monday, but when I loaded it up today after work, I saw that the model's files were actually corrupted, specifically the RDS file, so I actually have to rerun it all over again, unfortunately, which is not great. But for this video, I've wanted to mostly focus on the modeling concepts and modeling frameworks, and not the actual results for the models. So although it kind of is disappointing for me, just because I wanted to kind of show you all of the results from all these models, but I have to start from scratch. But for right now, for this video, I don't think it's really going to impact it. And maybe I'll go over the actual model results in our next video, which will go over the actual deployment and dashboard creation. So that's a little disappointing, but I'm still going to go over the feature engineering and actual modeling, but we might not see as many results, and we'll be focusing mostly on more of the frameworks and the kind of thought process that goes behind the actual modeling standpoint. So I don't think it's too big of a deal, but unfortunately, I screwed up and I messed up my component models, and I have to retrain them again. But that's fine. So let's actually go over the feature engineering part. So if we remember from my previous video, we basically scraped all of our data, cleaned it up, and we selected some relevant stuff that we wanted to mess with. So I'm just gonna go line by line and just kind of explain what I was doing. So obviously, I just load in our fight data that was all cleaned up, and basically this entire feature engineering script is like one or two code chunks. And the main ideas behind these features that I wanted to create was, we basically want to have your basic fighter statistics and analytics and stuff like that. So the average punches thrown, average punches landed, total strikes absorbed in this entire career, stuff like that. So that's pretty easy stuff to implement. But one of the things that I think was interesting that I wanted to add is some helper functions. So when we're creating these models, we want to make sure we don't have any data leakage. So if I'm trying to predict a fight, I want to include the strikes thrown for that fight to predict the outcome, right? So because that's not going to happen already. It's not going to happen. Instead, we're actually going to use this model to do like hypothetical things. So for example, for this next Saturday, it'll be Gilbert Burns versus Kamaru Usman, and we don't want to use the Kamaru Usman versus Gilbert Burns fight to predict the actual outcome if we've never observed it. So that's why I use a bunch of lag functions. So just taking the fighter's previous fight that we've observed to use as like an input. Okay, so that's just kind of to prevent a lot of data leakage. So most of these functions are kind of being wrapped around a lag function. So I created a lag sum and also a lag mean. So let's actually start going into the code. So we have a fighter table that I'm trying to create, which will basically combine head-to-head stuff. So an opponent and a fighter. I obviously do some, just some data cleaning just to convert to ones and zeros, just in case if I need to do anything. One of the things I also added was I want to basically consider a fighter being different when they're in a different weight class. So I think if a fighter drops down or goes up weight class, the general fighting style changes a little bit. So, for example, for bantamweights or the 135-pound guys, they're going to be throwing way more volume than, say, a heavyweight fighter, right? So stuff like that, where I basically have it grouped by fighter and weight class instead of just fighter. I also arrange it by date, since we're going to use these cumulative functions. That I figured it'd just be a little bit easier, just to make sure there's no weird window functions going on. So I create basically some win features. One of the win features that they had was that we could basically have like win by um, TKO, win by decision, etc. So this basically converts as like a one hot encoded feature, where you just essentially assign a one, and then a pivot wider where it's saying that okay, whatever value they have, we're gonna say that's a one, and for the remaining values or remaining options that you can win or lose by, we're just gonna replace it with 0. Nothing too crazy. And then we start doing is, we do our lag functions where we're basically summing up our cumulative wins and losses by type. Okay. One of the things that we also have is like number of fights, since we have to always consider or think about how we're always using a grouped um, data frame. And I think one of the problems with this entire feature engineering pipeline is that it's doing a lot of most of the manipulations that goes into the actual feature engineering is a group by, and that can basically slow the actual function severely. So this is actually a very slow script to run when you consider that a lot of it is just doing basic lag cumulative functions, stuff like that. So one of the first things I did was, total wins, total losses, total rounds. So if someone has fought a bunch of rounds, you could see that, maybe that they're kind of more of a veteran. They have more experience, etc. And obviously, since we're going to be using some more non-linear models, that we can actually have some type of thing where up to a point of total rounds or up to a certain amount of seniority, we can see that the fighter is more likely to lose. So if a fighter has fought like 300 or 400 rounds, he or she is probably an older person and is probably going to be retiring soon. So the model could see that and say, oh, they might have less output thrown, or they're just more likely to lose. Okay. So again, I created your generic damage feature. So it's saying like total strikes absorbed, total knockdowns, total significant strikes absorbed, all these things that, I think is pretty straightforward. It's something where like, yeah, a fighter is going to have a bunch of damage throughout their career. And I think that damage can have some impact in the future. So just having these like total damage features, I thought was pretty useful. So a bunch of it was just, summing everything up and then creating some proportions. So like strike accuracy, significant strike accuracy, takedown accuracy. Just see like, okay, when they go for some type of offensive maneuver, how likely or what's the probability observed, percentage observed, actually landed. So we could see someone who's like, someone who has a high amount of strikes attempted, the high probability of landing, as a volume striker, and they could be a little bit better than, someone else. There were some missing values just because we're using like some lag sum. So we just converted to 0. I did 0.0 because they were like doubles, and that could help kind of circumvent that data type. Additionally, I wanted to see like, okay, if a fighter has outstriked his past fighters, let's just calculate their differentials. So just trying to calculate, the total strike differential, the average differential, just to see like how good is this fighter, one of the things that we talk about, I guess, in UFC is, you want to hit someone and not be hit. So that's kind of just measuring out the differentials. And then we also have like a day since last fight feature. I'm not sure how actually useful this is. But you could say that, a fighter hasn't fought in a long time. They could be rusty, so they could have like less output. Or if a fighter fought really recently, that could impact him with the weight cut and stuff like that. Again, then we remove like rounds, time, date, last fight date, just because we don't really want to incorporate that into the model. And then I use a mutate across. And this is one thing that I wanted to add. Instead of just having a simple average, which we have been doing already, I wanted to do some type of weighted average. And in this case, I think this could be definitely like changed a little bit. So the idea is, maybe we're gonna have more of a weight towards a fighter's most recent fight, right? A fighter is as good as his last fight. So we add a weight basically to the features for like significant strike attempts, significant strikes landed, etc. All these offensive generic UFC metrics. So I added a lag basically to it. We have and I basically said like, okay, we have like this lag 3. So if the fighter hasn't fought 3 times, or if the fighter has fought 3 times or stuff like that, we apply different lagged formations. If there is just like only one previous fight, then it'll just give it the default, right? So it's just kind of saying that like how many times has this fighter fought, and if he or she hasn't fought 3 fights, how can you adjust this weighted metric? Um, Ideally, I think this model works. The model that we're creating or that I want to create is basically going to be more about more experienced fighters. So for me personally, I would probably just filter it towards main card fights. So on a main card fight, if you're fighting on the main card, generally you have fought a few fights to make it onto it, or you're like Michael Chan or who got traded into it. So for that, I think that way we'd have more information. Additionally, if you have a main card fighter who doesn't have a lot of data, I'm sure this model that we're creating is going to estimate that fighter just because there's not a lot of information on a fighter, and it doesn't. It's not, and the fighter's not really in our data source that we're currently scraping. So I could incorporate like Bellator and stuff like that, but for me, just because this this entire video series is about like a simple project that I've basically only worked a few days on, a few nights on, after work. So I don't want to put too. I don't want to say I don't want to put too much effort into it, but it's something where the amount of effort I put into it kind of defeats the point of this entire video, where I really want to teach, what the thought process is of the video. It's not really about creating great, fantastic Oracle 538 style product. It's more about getting into it and showing how to create a little side project for like a resume for a student. Okay, with all that rambling aside, we're gonna go on to these these features that I also created. So these are just basic lagged features. So I just say like, okay, what was the previous fighter's um strikes thrown and stuff like that. So I also want to basically incorporate some AR models into it. So this entire model has a bunch of like moving averages, total intercept averages, and then it also has a lagged features. So it's kind of like an ARMA style forecast where it has all these different components. You may also notice that we're actually creating like a lot of components for this model. Like if we were to create like a linear regression for this model, it would definitely not be great because all of these features are going to be correlated. There's a high dimensionality, and it's something that it's not made for your traditional linear regressions or logistic regressions. Well, I guess you could probably do a logistic regression, but it's something where what we want to do is start creating a bunch of these features that we have a hunch that would be kind of useful for predicting things, so that we can then regularize and kind of remove some features that we only need. So with that being said, we basically did all of these things where we basically created your generic totals, your averages, percentages, your differentials, your weighted averages, and your lagged features. Okay, so that's all good, and then we just kind of ungroup it. We remove some things that we don't need, which these things are the actual values that happened in that fight that we're actually trying to predict, like outcome, strikes, takedowns, submission attempts, etc. These are things that we actually want to use or we want to predict. So we don't want to have this into our model data yet. And then we do that. So right here, as you can see, we have all of these features about like, what is it, 143, I guess. And you might be a little worried to see that all these are zeros just because these are their first fights. So if it's your first fight, your average is obviously not going to be greater than 0. So they're all zeros. So stuff like this, where we have a bunch of zeros, that's something where I would consider just removing these and just having like some type of filter where we're going to require to be in the model and to be predicted, you might have to have like 3 or 4 fights. Okay. One of the things that I actually think adds a lot of value, or one kind of different take on your traditional UFC models that you see on like Kaggle, is I added an ELO feature. So since we have some experience with ELO, the ELO package from my previous UFC videos, I decided to actually use that video and kind of run an ELO model, and then use those ELO values as a feature for our data. What that means is I think this is good because we already have a bunch of auto regressive features with the lagged values. and we also have like the total wins. But one of the things that we really want to, I guess, measure empirically is how great were these wins for this fighter, right? If a fighter beat a guy, was he expected to beat that guy? And that's why I wanted to add an elo model into it so that we have some type of measurement of it. So generally, what we also want to do is basically kind of like outperform an elo model at least. So if our model isn't outperforming an elo model, then our model is basically pointless because an elo model takes about 5 seconds to run. Um, so that's one thing that we kind of wanted to add. It was just kind of like ensemble and elo model. That way we can quantify how good our fighter is, how well the fighter can upset fighters, and when he or she beats a fighter, how much better was that fighter, or how great of a win was it? So that's what I have right there. And then we have 145 features. So we added a few more, which I believe was just like elo. I think it's just elo, right? Yep, elo and then elo change. So like what was the previous change, stuff like that. And finally, what I did was basically, since this is just one fighter's metric, so each fighter has about 145 features. We're basically going to combine them with each other. So the fighter and opponent are going to be doing the head-to-head table, stuff like that. Again, we also said, like, okay, obviously a fighter cannot fight him or herself. We remove the weight class, opponent weight class, and the opponent res. I kind of want to still include the weight class. I know I might include it in the model. But once we actually get into the modeling standpoint, I'll show you why it's not in there. But we can, if I don't like the actual component results, I'll probably add weight class because I think weight class could add maybe some help to the model. But to be honest, I think one feature out of all these other features might not add that much effect, especially weight class. I'm not exactly sure. So I added some more differentials. Now that we have our elo data or our elo feature, we can say that, you know, if one fighter has a higher elo, then that person is favored. So that is a good feature to have. You know, if a person has a higher elo score, they're more likely to win. We can also calculate the differential to basically see like, oh, how much more likely is it the fighter gonna win? We also have like the differential between the number of fights. So if one fighter has more fights than the other, they're more likely to be like a veteran. And then we combine the elos together and calculate the elo probability, just to, you know, skip some steps in case if our model can't calculate it itself. I also created a few metrics by hand that I thought were interesting. So the strike metric, opponent strike metric, it's essentially saying like, oh, if someone it's kind of calculating using a Laplace transformation from the like strikes landed versus strikes received. So like a Laplace correction on the strike differential, and then also multiplying it by how many KOs or TKOs the fighter had. So if a striker outstrikes, usually outstrikes his or her opponent and has a lot of wins by TKO or KO, aka if they can outstrike their opponent really well and they have a lot of knockouts, they have a high strike metric. And then I calculate the differences between the strike metrics, and then I have the strike favor. So if someone has a higher strike metric, then they're favored. Additionally, I also have like some submission metrics, just because I think submissions are a little bit more interesting. So, you know, if they take down, if they have a high amount of takedowns, so if they're really good at taking people down, and they have a lot of wins by submission, they have a very high submission score, right? And also, I also kind of combine the takedown defense with the lost submission. So if they haven't lost a lot, if they've like say if they've never lost by submission and they've defended a lot of their takedowns, that's very good for our submission metric. Okay, so we basically create some a strike metric and a submission metric just to measure just how good of a striker they are, how good are they at submissions, just to kind of think about, you know, maybe these are some interesting features to add into a model just to do some feature engineering and some interactions. And that's basically it. So this is about a 298 column a table. There's 11,000, about 12,000 fights. You also have to know that these fights are duplicated. So there's a fighter and an opponent, but these opponent and fighters will switch. We have to keep that in mind when we're actually doing the modeling. So that's basically it for the feature engineering. That was kind of my entire mindset. I don't think it was too crazy of a feature engineering. Mostly just like, you know, doing your totals, your averages, your weighted averages, your differentials, and then you kind of do some kind of cool interaction metrics. Additionally, we also have incorporated some elo models to assess, how the quality of wins against his or her opponent and the quality of losses, while using also like a baseline model to predict the probabilities that could also add some type of effect into our downstream models. So that's basically it for the feature engineering. Okay, so now we're actually going in the modeling part, which I think the modeling part is the most interesting. So first, let's actually kind of go over like how would we approach this from a modeling standpoint. I think from a lot of the videos that a lot of the the notebooks and scripts that I saw on Kaggle, because creating a UFC model to predict fights is not a new concept. Same thing with like predicting baseball wins or baseball runs. All these things centered on sports is not a new idea, and chances are you're not gonna be the first person to think of a sports idea in sports analytics. But that being said, when I read a lot of these UFC notebooks, a lot of times what they do is they scrape from UFCdata.com. They grab everything, they put it into a little tensor. They use Keras to predict the outcome of the fight using binary cross entropy, the sigmoid activation function. I think that's cool. I think that's fine. One of the problems with this, I think, approach where you're essentially creating a black box oracle, where you're just shoving all these features in and having the model basically kind of overfit and predict the results, is it's not a good way to model things when you want to kind of validate it. What I mean by that is obviously you can do some type of Lime model and PDP plots, stuff like that, to gain some type of interpretability from these neural networks. But it's not exactly the most, it's almost too direct, where you're having the model do all these things that you can't really validate and check. So for my approach, just to make it a little bit more interesting, and I think because it kind of adds a little bit more from and builds upon what we've been doing in my entire TidyTuesday series, is we're just gonna model out the components and use those components as an ensemble to predict the outcome. So we're actually gonna do a bunch of models. I still am gonna do a bunch of neural networks, and I think one thing that we can always do though is putting all these putting everything into one tensor, and then in a tensor format, and then predicting an outcome like we see in all these other Kaggle books is relatively easy. Like, right, we have our fight data, it's already processed for that approach. So if anyone wants to do it, they should do it. It's there for us to do it. So definitely not saying you shouldn't do it. It's just something that I didn't feel like doing for this project, because frankly this video would be 5 minutes long. So let's actually go over what I was doing, even though with me being highly critical about these modeling approaches, me screwing up the entire process and having to restart this video, restarting my entire training process for these components, where I don't even have it finished for my actual video on machine learning. So that was a lot of rambling, but let's actually go through this. So we're incorporating our fight data, our fights, and our fighter tables. These are just kind of our main things that we want. The fight data is, the pre-processed feature engineered data set that we were kind of working on. I mean, this was like the one that we were working on with our feature engineering. And then we have the actual fights, which is the processed post feature engineering data set. So one of the things I first wanted to do was actually create a components data set. So what this means is I'm basically trying to predict certain components. So what I want to basically want to predict for each fight is, knockdowns, significant strikes landed, submission attempts, takedown landed. Right. So I'm basically trying to predict, like, okay, how many punches landed is this fighter going to land when he's facing this other fighter for this fight? So I have this target components where I basically say, okay, I'm going to select the fight PK, the fighter, round finish, and also the things that we wanted to do. I actually don't need these attempts, because I was when I was actually originally doing it, I was thinking, well, maybe we can model the attempts, the landed, everything like that, just to validate, just to make sure, like, our attempts are always higher than our landed. But I don't think that actually adds a lot of value for right now. So I wanted to just do the actual landed part. And for submission attempts, there's no submissions landed, because if they actually landed the submission attempt, that means they won the fight. Okay, so I actually can remove these things, but I'm just gonna leave it in just because like this script is still going, so I don't want to bug that. Okay, so we have our target components, which is essentially the thing that we're trying to predict. And then we have our independent or individual components, which is like the components that are not the target, right? So all of the stuff that we created from our feature engineering script is right here. Did a few bunch, did a little bit of cleaning, just converting things to factors, also removing things into like if it's a 0, it's like it's NA. Okay. I mean, I replaced any NAs with zeros. Sorry. So one of the things I did was I actually wanted to create a outcome model. So one of the ideas, right, is, instead of putting everything together into a model, realistically, we want to kind of replicate the real world. And if we think about when we're assessing a fight, or how a judge assesses a fight, if a fighter outstruck his or her opponent, had more takedowns, had more knockdowns, had more significant strikes, had more submission attempts, the fighter should win, right? The fighter should win. So what I essentially did was just created a differential data set. So for the actual inputs, so it's saying that I did a pivot longer, and then I said, okay, we're just going to calculate the fighter's component values minus the opponent's values. So that's like the differentials, right? So it's saying like, okay, so this diff is like strike diff. So that means if it's positive, that means the fighter had landed more strikes than the opponent. Additionally, what I actually did, let's see here. So that's basically all that stuff, where I just calculated the strike differentials, or the I guess the target component differentials for the fighters and the opponents. I also wanted to remove any matches that resulted into a tie. I figured incorporating ties inside a model isn't really the best idea. I don't think a lot of people predict ties or draws, because I think they're relatively rare in UFC. So I just removed that. Additionally, with the data frame is, we know that we have the opponent and fighters have this pairwise swapping effect, where if fighter A is fighting fighter B, those pairs will actually swap, because we have duplicates. So I basically grouped it by each individual fight, and then sampled a random fight from it. Then I created, again, just doing some factors stuff. So it's saying like, if it res equals 1, it's a win, else it's a loss. Okay. And then one of the things I also added, just as a little feature, just because I think this would also help a lot in the model, just saying like, let's count how many times the fighter has a higher differential, or let's count the total components that the fighter outstruck or outperformed his or her opponent. Because this entire model is trying to predict the fighter's outcome, not the opponent outcome. So that's why we don't have like, we don't have the opponent's total advantage, or total components that they had an advantage on. So we just say mutate across. If it's greater than 0, that means fighter outstruck or out through his or her opponent. So then it'll be like, knockdown advantage, strike landed advantage. And then what we do is actually a row wise. We use a row wise function for every row. We just sum across all that stuff to get the total count that's above 0. We could also manually do it, but for me, I think this is actually one of the more elegant ways to do it. I'm sure there's a better row wise function to do it, but I actually don't really use row wise a lot. Okay. Again, I don't really want to go too much into. Sorry about that. I do like the tidy models part. I've made a ton of videos on tidy models. I think obviously I'm going to still go over, but I don't think I have to go too much into detail with it. Create my training test splits using k-folds cross validation. Create a recipe removing the fight BK and the fighter. Just do a Yo Johnson normalization with it, and then since this is a classification, so we're basically using these strike differentials to predict the outcome of the fight. We have our accuracy, ROC, sensitivity, specificity, mean log loss, control grid, saving the predictions just to see where the model went wrong, stuff like that. Also to view some confusion matrices. In this case, I also wanted to use XGBoost for the classification. I wanted to use XGBoost for all the models, really for no particular reason. I think actually, I would probably change it to random forest for the components models, just because the actual component models have a very wide data set, which will definitely benefit random forest more than XGBoost. But I'm not too worried about it. If I see bad results in my actual tuning process, I might change it to random forest, or it's something that you guys can do in your own time. Then I tuned the models and I saved the outcome. I actually saved all the outcomes because I was playing at the end of the video to basically evaluate all my models and basically say, okay, here's our model performance for this metric, here's our model performance for this component, etc. Okay, so right here, we basically finish our outcome model, which uses basically the differentials for that fight to basically predict the outcome of the fight. So if this fighter outstruck, had more knockdowns, had more takedowns, had more submission attempts, then that fighter is more likely to win. So now what we're actually doing, which is probably the majority of this actual script, is now we want to actually predict, a fighter's knockdowns for a fight against another fighter, right? So we did that. I created my train test splits for all these components. Now we can see what we're trying to predict. We're trying to predict target knockdowns, target significant strikes landed, target strikes landed, target submission attempts, target takedowns landed. And I totally did not go over one thing I added, which is right here. So one of the things I was thinking about, and one of the things I actually messed up while I was working on this script a week ago, was I didn't really normalize our targets. And what I mean by that is these targets are the entire total fights component. So it's the total strikes thrown in that fight. One of the problems with this is that fights end. Fights can have multiple rounds, right? So a fight could have 3 rounds or 5 rounds. Additionally, if a fighter knocks another fighter out, it stops at that round. So some fights would have way more strikes landed than another fight. And I was thinking, well, we could model it out and just leave it like that. Or what I could do is basically try to predict the average strikes landed for a round, right? The average knockdowns per round, the average submission attempts per round. So that's what I basically did right here, where I basically said, like, okay, for all of these outcomes for the fights, we're gonna basically normalize these components by the total rounds that were actually fought. So we're basically we're trying to predict the average strikes landed, the average knockdowns, the average takedowns for every fight. And then we can also multiply it at the end, like when we're starting our dashboard. So that's why we have like target takedowns landed, where we're trying to predict 0.5, right? There's no such thing as a half a takedown. It's just because, it went 2 rounds and there's only 1 takedown. Cool. So one of the metrics that I just set was RMSE, MAE, R squared, MAPE, SMAP, PE. But the main metric I'm really looking at is RMSE, or root mean squared error. For my tuning function, I actually wanted to go with the fine-tuned package because I was pretty lazy about it and figured that, having simulated annealing, or whatever it's called, would be kind of beneficial for me for this project, just because I didn't really need to define a parameter grid for all these components. Instead, it could basically search for it and it could stop early if it found it. So I basically defined all these models since they're all using the same data set. I didn't want it to include all of these, this data leakage right here, where we don't want to include the fight PK, the fighter, the actual strikes landed, the actual significant strikes landed for that fight. We want to remove that and then predict, total knockdowns, right? Did Yeo Johnson normalized one high encoded the stuff. Did the same for knockdowns, significant strikes, submission attempts, takedowns, and we removed all the things that were the targets besides the target that we're trying to predict, obviously. So that's basically it right there. And then again, define another XGBoost model. In this case, I think I wanted to try, and I still might do it. I might try a random forest model, just because we can set, even though it's obviously a tree-based model, I figured, why not try random forest, because I think random forest and XGBoost will generally have similar performance with each other, so there's no reason not to try it. And then I did tune, sim, anneal with 5 iterations using k-folds cross-validation. And I'm saving out all these outcomes right here. So that is basically it for the XGBoost individual components models. Which I think, if you actually look at it, I think it's pretty straightforward. I think it makes a lot of sense. Because we're basically trying to output like each individual's fighters components, use that as a thing for the phone use that to predict a fighter and an opponent's strikes and knockdowns, calculate the differentials, throw into the outcome model to basically be the judge and say, okay, we see that this fighter outstruck this fighter, we're gonna say that fighter won. Right? That way we can validate where it's like, oh hey, like, why is it saying that Dustin Poirier is gonna beat Conor McGregor? Instead, we can say because our model is forecasting, Dustin Poirier to have, 20 more significant strikes than Conor McGregor or something like that. But we also want to do some neural network stuff, right? So with neural networks, we got to do a little bit of pre-processing, but not a lot. So again, we have our inputs and our outputs. So in this case, we have like our output is we're trying to predict knockdowns, significant strikes, submission attempts, takedowns. And then our input is not anything that has a target 5PK fighter. Then we do some pre-processing, EO Johnson, normalization. Then we do step range to convert it all in between 0 and 1. We do dummy, 1 hot encoding, and then that's it. Okay. Then I basically apply that matrix or apply that pre-processing to the inputs and outputs and convert it to a matrix. Same thing for the outputs. So I define a basically a, your generic 3-layer densely connected neural network, pilot using Atom, mean squared errors are loss. I want to see the mean absolute error. And here's the one thing that we kind of get into where it's actually pretty interesting to do some of these multi-headed neural networks, because instead of doing all of these components individually, I wanted to do all these components at once. So we actually have, 5 nodes, right, for our output. And these nodes are going to be predicting our 5 components that we want to predict. But what we have to do is when we're calculating the mean absolute error, we have to, or calculating the mean squared error, we have to realize that these outputs, so knockdowns, significant strikes landed, submission attempts, and takedowns, they are on different scales, right? So if we're off by 30 for knockdowns, but we're only off by 1 for significant strikes, it's going to have that it's going to basically have that basically the same, unless if we start weighting things. So one of the things we have to think about is, what thing do we want to really focus on to be highly accurate for a model? And one of the things I did was actually looked at my outcome model using the differentials and basically looked at the variable importance. So I saw that right here. Where is it? So with our differential model, calculating all the differentials between all the components, I said, what is the most important variable for this component? And it said that basically significant strikes was the most important component. And realistically, that's something what we would expect, right? If someone has a ton of significant strikes advantage or had 20 more significant strike attempts than significant strikes landed than his or her opponent, the fighter's going to win, right? So that's basically what I added. So I kind of just calculated a random weight and said, okay, we want our significant strike landed to be very accurate. Knockdowns, we don't really care that much. We could say, and then was it takedowns? I said, you know what, maybe we'll decrease that weight. This is something where I was like, okay, this is completely arbitrary. We just want to kind of, make something up. So I did that and waited mostly towards significant strikes landed. Then it'd be followed by strikes landed. Then it'd be followed by, submission attempts. Then it's followed by knockdowns and then takedowns. Okay, so then I fit it using a validation split, using early callbacks. So the epochs or epochs don't really matter too much. Basically, it's saying like if we don't see any improvement after 20 epochs or epochs, it's just gonna stop early. Cool. So I did that. I thought that was okay. That's fine. It worked. This is mostly for actually seeing like, oh, how well does this multi-headed model work? It worked. I didn't run into any errors. So then I started creating an actual validation index. So using my training data, I wanted to create a validation split for our training data because I didn't want to touch the test data at all. And one of the things I wanted to do now is actually basically tune these weights. So, how much should I actually weight my loss function to each component, right? So I created a function basically to tune the Keras weights where it creates a model where your only input is a vector of weights. We say, okay, we can give it any weight, so add weights to the outputs. And then what's actually doing is it's using that validation data from our training data to basically predict the mean absolute error for all the components, right? So it's actually predicting on our validation data that it's never seen, and then I'm calculating each component's absolute average error or mean absolute error for each component, right? So I did that. But one of the things I was thinking about is, well, I need how can I simulate 5 weights where I want it to equal 1, right? And that's like the Dirichlet distribution, Dirichlet. I know this is like German French, so I'm terrible at that. Even though I took a year of French, but it's like the Dirichlet distribution where I just use the gtools package to basically get a vector of 5 values randomly that sum up to 1. So I basically said, okay, we're gonna go through this. We're gonna simulate 50 random weights, and then tune 50 models, and I basically get the each component's mean absolute error, right? Then I removed that, summed up we also had the total error, so total absolute error, and plot that out. And what we actually found, obviously, is that we want to weight more towards these values again. So instead of just having a uniformly random, I wanted to add a little bit more weight towards significant strikes and also knockdowns. Had it simulate, and then we can see right here the density of our our error or whatever. Yep, our total error. And then we could see which one had the lowest error, and these are the weights that I wanted to use, I guess, for my actual final model. So instead, we actually changed more towards V2 and V5. Cool. So that's basically how I simulated it. I just wanted to say, like, okay, what's the mean absolute error for all the components when we change the loss weight scheme for all of our components, right? So that was a quick and dirty way of basically having some type of informed decision on assigning weights to our actual model to predict the target components. And that, to me, it kind of makes sense, but also I'm a little fuzzy on it because this is really assessing like each component's absolute error. So how well a neural network can fit to the actual component. So how well it can predict strikes thrown, stuff like that. It's not really doing like total, the actual outcome of the match. Right. So right there, I fit my final model, where I basically want to try out, since I was basically using I'm kind of all over the place. I was basically using, a generic 3-layer 512 unit wide neural network, which is, it's not, it's something where if you had that, you wouldn't know if there was a better model. You'd want to at least tweak and see how well it works with different little architecture. So using the same weights, same training data, same scheme for callbacks and stuff like that, I essentially created a few different neural network architectures. One, adding dropouts, one just making it a little bit wider, and then one just adding it, making it a little bit deeper and wider, right? So all that went down, and I basically recorded all of it and saw that the simpler model, I guess, had a little bit better. What is this? Actually, I don't think I needed that. Let me see. Okay, yeah. So I found that I think this model had the best validation error using the validation split, assessing mean squared error. So I just fit it using a slightly wider model with dropout. Cool. So one of the things I was also thinking about while making these models, especially with these multi-headed models, is so we have this model predicting five features, right? It's trying to predict takedowns, knockdowns, submission attempts, strikes landed, and significant strikes landed, right? All of these this is just our simple regression problem. 5 regression models basically using one neural network. But I was also kind of thinking about, what if I did a different multi-headed model where instead of just trying to predict these 5 components, what if it also tried to predict the outcome of the match, right? So while I was reading, was it deep learning with R? A lot of times they were talking about, like, when you're trying to predict, an image, saying like, is this a dress? Is it a shoe? And also trying to predict the price. It was actually better to do one model that did both things, where it did both a classification and a regression problem, instead of having 2 different neural networks to do that task. So I thought, okay, well, what if I just add in the outcome of the fight, and let's also assess, how well it fits. It'd be kind of cool if, like, it could predict the components better and also predict the outcome better, right? That'd be pretty cool if it did it. So that's what I did. I essentially created another output where, instead of just having these 5 components like target, knockdown, significant strikes, etc., I also added the outcome, converted that to a binary outcome, 1s, 0s, and then convert it to a matrix. Okay. So I did that for the train output and the test output. Still going to have the same inputs, just going to have slightly different outputs. One of the things I had to do, though, is not use the generic high-level interface. Instead, I had to go a little bit lower level, but it's still Keras, so it's pretty easy. So basically, I had to define an input. These inputs, we knew what our input dimension was, which is the total columns of our input. So I just said player input shape is equal to the total amount of features that we're inputting. D-type, integer, name, fights. Right, this is our fight input. Then I defined a base model. In this case, I wanted to do a 3-layer neural network, and I wanted to add dropout. I guess I also should say that I use ReLU activation functions for all my models. I think I've just always used ReLU instead of, like, all the other things, like, was it softmax and stuff like that? The softmax, it's the TANH instead of, like, TANH and stuff like that. I've always just used ReLU. I think when I was reading more about neural networks, that was when it was really the ReLU activation function was really in fashion. So I just did that. Then I had to basically define all of these outputs. So I said, like, okay, for knockdowns, significant strikes, submissions, takedown, landed, all of these are just one unit because it's a regression problem, right? No activation because it's a regression. But for the target res, which is the outcome of the fight, it's still one unit. But in this case, we apply an activation, which is a sigmoid activation because it's a binary outcome, right? So after that, I have my input, which is our fight input, and then our actually, it should be a base model. And then our base model, and then we add in our it's fight input when we're talking about, because the base model, these target KDs are assigned to our base model, right? We have our input, and then we have our other 6 models kind of being as our outputs. Okay. Then I compiled it. I used basically the same weighting scheme, except I added a 0.2 to the results. I also defined for our loss, like all of them will be mean squared error, except for our outcome, our results, which is, a binary outcome. So we use binary cross entropy. So that was how we defined it. And then lastly, I just fit the model using all these inputs, just from saying that, okay, we want our using our baseline input, and then our output would be our knockdowns from our output matrix, and just like index. So I decided to say 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Defined 500 epochs, a validation split of 0.2, so 80-20 split, and then applied early callbacks. And that was basically it for that model. Yep. And then what I was going to do, which I'm sorry, let me see if I actually have it. Nope, it's not done yet. Never strikes landed, knockdown tune. Yep, so I have a few more hours to go. So what I was going to do, basically assess all of the results for our models. I was basically going to say, like, okay, collect the one with the best RMSE for all these models, collect the one with the best ROC, AOC, or accuracy, because I wanted to view the confusion matrix, see that. But I would have suspected it to be pretty accurate, just because I think it'd be weird for someone to basically outstrike, have more knockdowns and stuff like that, unless if it's like a knockout, I guess, which can happen. But generally, I wouldn't want to model that or like overfit to that. I'd be fine with missing some from crazy knockouts. So I was basically going to do that for these individual models, and then and then use my neural networks and basically predict on the test set that we have, that I think all these models share, and using that test set, basically calculate which one had a better RMSE, our XGBoost component models, or our first neural network that just did the 5 components, or our second neural network that did the 5 components and the outcome. After that, fit them together and save them as a model file, as an RDS file, and then just continue on the actual app. So I think for next video, I'm going to be focusing on creating a simple little dashboard, probably a dashboard similar to the other dashboards I've made, but also probably implement more of like a pipeline and figuring out like, I guess it's mostly going to be dependent on the models that we have, but adding some interactiveness. So allowing a person to select a fighter and another fighter and calculate the probabilities, calculate spreads, and also have like be able to go to another page and download all their data, their generic data and stuff like that. So I know this video was actually very long. It's a 52-minute video where I essentially talked and rambled through it, but I hope you liked it. I'll definitely see you guys next week for the app, and I'm definitely excited to get some of your questions to answer for my Q&A. So with that being said, I'll see you guys next week, and tidy on.